All right, let's get started. So last time we talked more about sets and set operations, ways of combining sets and making new ones. And today we're going to talk about more about functions. And at the end, which I think we'll have time for, we will do another in-depth proof sesh. So there's another strategy for how to sort of get started and come up with proofs that I want to try to explain, give you an idea of. So we'll do that with a nice example of some function stuff at the end. But let's start with some basic recollections and function operations. So recall a function f from a set A to a set B is an assignment of an element of B to each element of A. And remember that we call A is the domain and B is the codomain. And I don't think I said this last time, but just to mention these words in case you hear them other places, you can also call this the source and the target, which maybe is more like natural words, but I think I'll stick with domain and codomain. And so I'm not going to recall the full definitions, but remember that we defined these images and pre-images. An image essentially means going forward through the map. So if you have an element of A or a subset of A, then if you apply F to it, you get an element or a subset of B, which is called the image. And the pre-image is going backwards. So if you have an element or a subset of B, you can look at all of the things that map to it, and that is the pre-image. In particular, so let me write this down. The image of F is the image of the full set A, which we can write as F of A for all elements of A. And there was a question at some point last time, what does the word range mean? And I said that it meant the same thing as codomain, but I want to adjust that slightly to say that range can be used to mean codomain or image. So in particular, it's a little bit ambiguous because those are different things. So I'm going to avoid using that term. So let's start in on some basic function operations. So first, we're going to start by considering functions whose codomain is the real numbers. And I guess later, functions whose domain and codomain is the real numbers. So these are called real valued functions if the codomain is R. And in particular, the fact that the codomain has operations of addition and multiplication means that we can define these operations on functions just by using addition and multiplication with things in the image. So let's define that real fast. Sum and product. So say we have two functions from some set for the real numbers. So they have the same domain and codomain. Then, and just to note, we could replace the real numbers with the integers or the rational numbers, basically anything where you can add and multiply the elements. That would serve just fine. But I'm going to stick with real numbers for now. So we can define a map f plus g, which is, again, a map from A to the real numbers. And it's just defined by f plus g applied to some element A is f of A plus g of A. So just to point out, we're using the addition in the real numbers, right? Because once we go through the map, we end up with a real number. So f of A is a real number, g of A is a real number. We don't need to be able to add elements of A. So A could be something that doesn't have addition. That doesn't matter, because we only need to add things at this end. And similarly, f times g from A to R by f times g of A is f of A times g of A. So again, we're just doing this multiplication in R. And this, you will hear this called pointwise addition and multiplication. Basically because we are adding the values at each point. So we're adding them pointwise. This probably is quite familiar, but let's just do some examples. For example, if f of x is x squared and g of x is 2x, so we're thinking of f and g as being, let's say, functions from the real numbers to real numbers in this case. Then f plus g is the function defined by sending x to x squared plus 2x. And f times g is the function defined by sending x to, I guess we would get 2x times x squared, which is 2x cubed. So, if you have a formula for your function, you're just going to add the formulas or multiply the formulas. Nothing too special going on here. So now let's say we have a function from the real numbers to the real numbers. In fact, let me give this a subtitle. We're going to talk about when a function is increasing or decreasing. So now we need a function from the real numbers to the real numbers, because now we're not thinking about addition, we're thinking about the order, and we want to compare the order on the domain and the codomain. So we need them both to be the real numbers. You could say this with rational numbers or integers, but these definitions are most natural for the real numbers because they are continuous and ordered. So f, like so, is increasing or strictly increasing if for all x and y, if x is less than y, then f of x is less than or equal to f of y. And for strictly increasing, we would say that f of x is strictly less than f of y. So you should think of this as saying that if you increase the input, then the output increases. This is why it's called increasing. And if it's strictly increasing, then the output strictly increases. And we can make a similar definition. So that's increasing and strictly increasing. F is decreasing or strictly decreasing if basically the same thing, except that this inequality is going to get switched. So this inequality we keep the same because this is just saying as we increase the input, what happens to the output? And in this case, the output decreases or strictly decreases. So let's just remember we're thinking about a function from R to R. F of x equals x cubed is increasing, and in fact it's strictly increasing. Because x less than y implies x cubed less than y cubed. And when we're thinking about increasing and decreasing, this is a great thing to try and think about visually. What does the graph of x cubed look like? It looks something like this. Happy with that graph, that's not the worst. So you can basically see that when you look from left to right, which is the traditional way to look at things, it's increasing, it's going up. And you will also note that it never stays flat. Now there is a slight subtlety in the sense that it does look flat for an instant when you pass 0, but as long as it doesn't stay flat for any length of time, it's still strictly increasing. So that's an example. Can we write down a function that is increasing but not strictly? We can. Here is another example. F of x equals bottom brackets x, which is the floor function. And what that means is round down. So if you put in an integer, you'll just get the same thing back because rounding doesn't do anything. So 2 is going to go to 2. But if you put in 2.1, you will still get 2 out because you round down. If you put in 2.9, you will still get 2 out because you always round down. You don't round up. That's what the floor function is. You go down to the next integer. So what does this look like on a graph? It might be easiest to see that it is increasing from that perspective. So if we're rounding down, then 0 is going to go to 0. So we'll put a dot there. And then everything between 0 and 1, not including 1, is going to go, well, I guess I'm drawing over the axis, so you can't see it. So 1 is going to go to 1, and then up to 2, it's going to stay at 1, and so on. And then this way, it's going to keep going. So this is an example of a function that is increasing, but not strictly. Because you can see that it does go flat. It stays flat. So you can get, so for example, 2.5. 2 is less than 2.5. But the floor of 2 is equal to the floor of 2.5, which shows that it's not strict. And then finally, let's say something like f of x equals x squared, which should be familiar. Looks like this. Well, all right, put in a little bit of effort to make this look decent. Oh my gosh, so hard. Drawn on the screen. Okay, let's take that. It's not so bad. So you can see that here it's decreasing and here it's increasing. And when we're talking about a function being increasing or decreasing, we're talking about that happening over the entire function. So this is neither. And decreasing, so these are all examples of increasing. Decreasing works essentially the same. And in fact, let's even say, note that f is increasing or strictly increasing. If and only if. So remember the I with two f's means if and only if. If and only if negative f is decreasing or strictly decreasing. So if you took all these examples and just put a negative sign, you will get examples of decreasing functions.